Hello, hello. Thanks for watching today, the history of the periodic table. I hope you're all holding up well in quarantine. I got that corona hair, don't care. I also don't have my big whiteboard that I would have up at campus, and so I hope you guys are patient with that. Um, I watched your feedback from last time. Noted. Cut the fat, and so we're gonna trim a lot of this video down. Hopefully, 10 minutes. Hold me to it, right? But buckle your seatbelts because there's a lot. And so here we've got hydrogen, most abundant element in the universe. Then we've got down here all the alkali metals. Next door, we've got the alkaline earth metals. All these metals tend to be very reactive types of things, right? I remember hearing a story in high school about how they dropped magnesium in the toilet and blew up, and they always tell that story, I feel like. Transition metals are this large block of metals, and they're very conductive, right? You notice metal gets hot really fast and it cools really fast. That's because their energy levels of the electrons are close together, and so it can absorb, reflect. They're shiny, right? Gold. We love gold. Some other metals right here, and next door we've got our metalloids, which they don't belong up here, but they don't belong with the metals either, and so they get their own spot. Here we've got some other non-metals used in organic chemicals and reactions. Here we've got a group called the halides. And the halides are very reactive. They're at 7 electrons. They want to get to their 8th electron. And so they want to react. And then last of all, we've got the noble gases. And the noble gases are very unreactive because they've got that complete valence electron shell. And so, organization, why am I talking about all this? What I want to impress on you guys today is the fact that when they devised the table, they didn't know that there were 8 valence electrons. They didn't know that there were electrons or electron shells because they didn't know what it was, or a neutron. They didn't know anything about any of that. They might have had an idea of a proton, but they didn't know about the nucleus or nuclear theory. And so devising the table, they had to say, wow, this one's kind of crumbly and kind of powdery, or they had to say this one's really malleable, and the transition metals are shiny. They said, and they kind of got to piece it together, and they did their best, and really they did a phenomenal job. Everything I've highlighted so far, these are called families. Families are similar things with similar characteristics to each other. Columns on the periodic table are called groups, right? And the same groups have the same amount of valence electrons. So 8, 7, 6, 5 valence electrons. Across the periodic table, we've got rows, also called periods, periodic. Let's talk a little bit about trends, right? Trends on the periodic table include across the table, they get smaller, which you think that's kind of backwards, right? If they're also getting heavier as they go across, right? The reason they get smaller is because all those protons and electrons close to each other draw the whole thing together. As you go down, though, they get bigger. Atomic radius goes up. And the reason for that is because every time you drop down, you add a valence shell of electrons, right? We've got an atom with these shells, and every time you go down, you add a shell, right? Also forgot electronegativity. They get more electronegative and higher electron affinity as they get over here, because on this side, they want to complete that valence shell. They want to get electrons from others. Over here, they want to shed them, right? So here they hold them tightly. Here they hold them loosely. All right? So let's talk some difficulties with the table. Transition metals follow the 18 electron rule, right? Usually we think of electrons having the octet rule. They want to get to 8 valence electrons. Well, these have to get up to 18. And the reason is because they have this extra D block with 10 other electrons they need to fill in that outer shell. The table was devised in 69, right? But the noble gases weren't discovered until 1994 by Ramsey and Rayleigh, right? R and R, right? Lanthanides and actinides down here, I forgot to even point them out, but they weren't discovered until 1945 by Seaborg, right? If you were in your mission in like 2016, you probably missed the 4 newest electrons they dropped. 4 newest elements, because there's 1, 2, 3, 4 more. The last one is oganesson, and it's OG. Also, they're developing 2 more, 119 and 120, right? And they're going to come out pretty soon here. And so just the fact that it's growing, that it's not done yet. At the time they made the table, they didn't know several of them, right? So imagine they didn't know gallium or scandium or germanium, right? And so you got a piece of this table and they got holes in the table, throws everything off, right? But lots of difficulties putting this table together, and there were actually lots of people involved. If you've ever taken a high school chemistry class and heard about Mendeleev, obviously he's the big dog. He made the table. But around his same time, so many people doing the exact same research, and all their contributions are so important. And so let's go jump in the slide deck and let's talk about the solutions. And I want to focus on how they put the table together. Obviously, elements have been discovered over time, right? The first elements were discovered by alchemists who were looking for gold, and they discovered phosphorus as they were like boiling urine and weird stuff like that. Um, Ancient Egyptians used copper. There's been lots of development into atomic theory. What I want to talk about is the table, how they put the table together. Lots of scientists were trying to put something together. The first was Alexandre Emile Beguier de Chancourteau. I don't speak French. I'm sorry if I butchered that. But in 1862, quite a while before the periodic table was coming out, he built this screw. And the screw arranges elements around the screw. And by the time you get back to the same side of the screw, you see a similar element. So you see lithium here, and down below it, you got sodium. And down below it, you got potassium. And so amazing how he was already seeing this cycle of 8, right? John Newlands was on to a similar thing, and he decided to arrange in octaves, like in music, right? Piano keys. He stuck 8 of these together in little columns, and you think, wow, that looks like a periodic table. He got no credit. This guy got no love from anybody. They clowned him and made fun of him, which he was off on a lot of things, but he was also on to a big idea here. Julius Lothar Meyer, and this guy was actually contemporary of Mendeleev. They studied a little bit together, knew each other. If he had released his table a year earlier, he might be the one we talk about today. He's a big deal. And I want to talk about this graph. What he did was he took atomic volume, which we talked about atomic radius, and then he took atomic mass on this spectrum. And when he started plotting these, you see how the period just came right out, right? As he stuck these all together, as they get heavier, they hit this peak of volume, they drop and come back. And that's because of the trends we were talking about. In 1869, Dmitri Mendeleev, 1 year after Meyer, was playing cards, solitaire, and said, hey, this is an idea. We arranged these suits and numbers. What if we did the same exact thing with the elements? And so he put it together and did a phenomenal job. One of the things he's famous for is knowing where these holes were going to be. Germanium, gallium, scandium. He said, there's going to be an element here. I know there is. Henry Moseley, and I think he's another one of the biggest. And what he did was X-ray crystallography, or diffraction, X-ray diffraction of these nuclei, and discovered that atomic number, not mass, is how you're supposed to organize them. Where before they did mass and found it's not working, it's not lining up, he saw these X-rays bend at a certain amount according to how many protons were in the nucleus, and that's when the table got great. Sadly, he never got a Nobel Prize or went on, young guy, to do a whole lot because he went to World War I. I just want to put a plug for a great movie. Afterwards, a whole lot kept happening. Becquerel discovered radioactivity in 1886, and that opens the door for radioactive elements. Curie discovering radium and polonium at the exact same time. Chadwick discovered neutrons and isotopes in 1932. In 1932, Cockcroft and Walton split a lithium atom into 2 helium nuclei. In 1945, Seaborg identified lanthanides and actinides. I've got some fun facts. We already talked about a lot of them. The newest elements are nihonium, moscovium, tennessine, and oganesson. They just came out. They just named them. The last element is the OG, right? Some newer super heavy elements are theorized to be much more stable, which right now these are just lab elements that are around for nanoseconds and gone. They theorize some of them are going to get more stable. Who knows? Maybe there's more coming for us. There's no J's on the periodic table. Did you know that? More fun facts. They get smaller as you go across the periods we talked about. These ones that he predicted. Helium was discovered on the sun 3 decades before on Earth, which I think is amazing. It's a noble gas. And you can't detect them. They have their full valence electron. They're hard to detect here. Noble gases were denied entrance for years, even after they were known, because they didn't fit in anywhere, right? There's only 94 elements exist in nature. The rest of them are synthesized in lab. And here's a bunch of, we know vibranium from Black Panther, and there's actually a feminum in Wonder Woman, there's a whole Wikipedia page I thought was funny. And so just to wrap up this presentation, 2019 was the year of the periodic table, 150 years since it was devised. It's amazing. It's the culmination of chemistry, it's the culmination of physics. It all comes together. And I hope you can see the difficulties that they had putting it together, and that the amazing job they did reveals so much about atomic theory and about the reactions they make with each other. And I hope it's been an informational video. Thanks for watching.